Long before the Sahara became an ocean of sand, before scorching dunes stretched beyond the horizon and merciless sunlight hammered lifeless rock, this wasn't a desert at all. It was a garden, a sprawling network of rivers carved through lush grasslands where hippos wallowed, elephants trumpeted, and crocodiles hunted prey that would seem alien today. The sky roared with storms that fed vast lakes stretching like inland seas. Giraffes browsed acacia forests. Lions stalked herds of strange antelope. Humans painted these animals on rock walls, preserving images of a world so different from today's Sahara that the paintings seem like fantasy, except they're not. This wasn't millions of years ago. This was recent, shockingly recent. The Green Sahara thrived as recently as 5,000 to 10,000 years ago, and before that, it appeared and vanished in cycles stretching back hundreds of thousands of years. The transformation from paradise to wasteland happened so fast that animals and entire human cultures were swallowed by advancing sand, their bones buried beneath dunes that now tower hundreds of feet high. What caused this catastrophic flip? Why did one of Earth's most fertile regions become the largest hot desert on the planet? And what beasts walked this vanished world before the sands claimed everything? This is the story of the Green Sahara, a lost ecosystem that rose and fell with the rhythm of Earth's orbital changes, and the creatures that lived, adapted, and ultimately fled or perished when the rain stopped coming. It's a tale written in fossils pulled from beneath the sand, in ancient lake beds now baked into stone, and in the haunting rock art left by people who watched their world die when rivers carved the desert. The Sahara as we know it, endless sand seas, blistering temperatures, almost no rainfall, is geologically young. Rewind 10,000 years during the African humid period and the landscape was unrecognizable. Massive river systems, fed by monsoon rain stronger than anything the region receives today, snaked across what is now barren emptiness. The largest was a continuation of today's seasonal wadis, but these ancient waterways flowed year-round, carving deep channels through bedrock and depositing rich sediments that fertilized floodplains teeming with life. These rivers weren't minor streams. Satellite imagery and ground-penetrating radar reveal buried channels hundreds of meters wide, suggesting flows comparable to modern tropical rivers. One system, now completely dry, once connected the highlands of Central Sahara to the Mediterranean, creating a corridor for animals and humans to travel between northern Africa and sub-Saharan regions. Fish fossils found deep beneath Saharan sand include species related to Nile perch and catfish, proving these rivers supported diverse aquatic ecosystems. Mollusk shells, freshwater clams and snails litter ancient riverbeds. Their calcium carbonate remains testifying to waters that were stable, clean and abundant. The existence of these river systems was proven through analysis of sediment cores drilled from beneath the modern desert. Layers of fine silt and organic material, sandwiched between wind-blown sand deposits, show repeated cycles of wet and dry periods. Radiocarbon dating and isotopic analysis pinpoint when these rivers flowed most vigorously, during periods when Earth's axial tilt and orbital eccentricity shifted monsoon patterns northward, drenching the Sahara with seasonal rains that arrived with clockwork regularity. But rivers were only part of the transformation. The real key to the Green Sahara's ecosystem came from what those rivers created. Lakes. Enormous lakes. Some were shallow and sprawling, covering thousands of square kilometers. Others were deep, stratified bodies of water with distinct thermal layers, much like modern African Rift Valley lakes. The largest of these ancient lakes, called Lake Chad at its maximum extent, covered an area larger than the Caspian Sea. Sediment cores from its former bed contained pollen from reeds, papyrus, and floating aquatic plants, as well as diatoms, microscopic algae whose species diversity reveals water chemistry and seasonal temperature fluctuations. Fossil evidence shows these lakes weren't isolated pockets, but interconnected networks. During peak humid periods, overflow channels linked separate basins, allowing fish and other aquatic organisms to disperse across the region. Tilapia, lungfish, and ancient relatives of modern African freshwater species migrated through these waterways, adapting to fluctuating conditions as lakes expanded during wet seasons and contracted during dry spells. The mobility of aquatic life meant that even when individual lakes dried temporarily, species could survive by retreating to deeper refuges or moving to neighbouring basins. Around these lakes and rivers, vegetation exploded. Grasslands dominated the lowlands, supporting herds of grazing animals. Acacia woodlands and scattered gallery forests lined watercourses, providing shade and browse for larger herbivores. Pollen records extracted from lake sediments show dramatic shifts in plant communities over time, tracking how vegetation responded to changes in rainfall and temperature. During the wettest phases, tropical plant species pushed northward into regions that are now hyper-arid. Pollen from fig trees, tamarind, and even moisture-loving plants like sedges appear in cores taken from areas where today nothing grows except the hardiest desert shrubs. The transformation wasn't instantaneous, but on geological timescales it was swift. Orbital mechanics drove the changes, specifically precession of Earth's axis, which shifts the timing of seasons relative to Earth's elliptical orbit. When precession aligned summers with Earth's closest approach to the Sun, Northern Hemisphere monsoons intensified, pulling moisture-laden air masses deep into the African interior. Rain fell in quantities that would seem impossible today, sometimes exceeding 2 meters annually in regions that now receive less than an inch. Animal remains confirm the richness of this lost world. Excavations at sites like Gobero in Niger uncovered skeletons of hippos, crocodiles, and enormous fish buried in sediments that were once lake bottoms. These weren't isolated specimens, but entire assemblages representing thriving populations. Crocodile fossils are particularly telling. These reptiles require permanent water and abundant prey, confirming that aquatic ecosystems were stable for extended periods. The presence of multiple age classes among fossilized crocodiles suggests successful breeding populations, not just transient visitors. Human settlements clustered along these ancient shores. Archaeological sites reveal fishing communities that harvested abundant aquatic resources using bone harpoons, nets, and traps. Pottery decorated with wave-like patterns and representations of fish indicate cultures deeply connected to water-based lifestyles. These people left behind middens, trash heaps, filled with fish bones, mollusk shells, and the bones of turtles and water birds, painting a picture of dietary abundance that would be unimaginable in the same locations today. The rivers and lakes of the Green Sahara created ecological highways, connecting previously isolated regions and allowing species to spread across the continent. Elephants, antelope, and predators moved freely between the Sahel and Mediterranean climates, following seasonal rains and the flowering of different plant species. This connectivity meant the Green Sahara wasn't just an isolated paradise. It was a bridge, a crossroads where life from different African biomes mixed, competed, and evolved together before the sands returned and severed those connections forever. Elephants in the sand. Today's Sahara is hostile to large mammals, but fossils reveal that elephants once dominated the Green Sahara's grasslands and woodlands. These weren't modern African elephants, though they were closely related. The species that roamed the ancient Sahara included extinct forms adapted to fluctuating environments, creatures that had to cope with seasonal extremes even during humid periods, because the Green Sahara, while wet, still experienced pronounced dry seasons unlike equatorial rainforests. The most common elephant species represented in Saharan fossil sites is related to the modern African elephant, but showed morphological differences suggesting adaptation to mixed habitats. Tusks found in paleontological excavations show wear patterns consistent with bark stripping and digging for water and roots during dry months. Some tusks exhibit unusual curvature, possibly adaptations for manipulating vegetation types that no longer exist in the region. Tooth enamel analysis reveals diets dominated by grasses and browse, confirming these elephants were mixed feeders exploiting the diverse plant communities of the humid Sahara. Fossil evidence for these elephants comes from multiple sources. Complete skeletons are rare, but isolated bones, femurs, tusks, vertebrae turn up regularly in ancient lake beds and dried riverbeds. One remarkable discovery in Chad yielded an elephant graveyard where dozens of individuals died together, possibly during a drought when a shrinking water source became a death trap. The bones, preserved in fine sediment, show signs of scavenging by hyenas and other carnivores, offering a snapshot of the ecosystem's food web. Rock art provides additional evidence. Cave paintings and engravings across the Sahara depict elephants in surprising detail, showing family groups, adults with calves, and even behaviours like dust bathing. The artist rendered anatomical features accurately enough that paleontologists can identify species characteristics. Some paintings show elephants interacting with humans, hunting scenes where groups of people with spears surround a large elephant, suggesting these animals were both revered and hunted. The frequency of elephant imagery in Saharan rock art underscores their ecological importance and their impact on human cultures. Elephants shaped the environment in profound ways. As mega-herbivores, they acted as ecosystem engineers, knocking down trees, creating clearings, and dispersing seeds in their dung across vast distances. Their movements between water sources created trails that other animals used, effectively designing the landscape's circulation patterns. During dry seasons, elephants dug for water using their tusks, excavating holes that became life-saving resources for smaller animals unable to dig themselves. These elephant wells persisted after elephants visited, serving as communal water sources that concentrated wildlife and created localized biodiversity hotspots. But elephants weren't the only proboscideans inhabiting the Green Sahara. Fossil evidence hints at the presence of extinct relatives with different adaptations. Some remains suggest smaller elephant species or populations that evolved insular dwarfism in response to resource limitations during transitional periods when the climate oscillated between wet and dry phases. These adaptations demonstrate how quickly evolution can reshape large mammals when environmental pressures mount, though ultimately none of these specialized forms survived the Sahara's final desiccation. The disappearance of elephants from the Sahara tracks closely with environmental collapse. As rainfall declined and vegetation zones shifted southward, elephants faced shrinking ranges and increasing competition for dwindling resources. Populations fragmented, isolated in patches of suitable habitat that gradually dried out. Some herds may have migrated south, merging with populations in the Sahel and eventually contributing to modern elephant lineages. Others likely perished as their last water sources vanished, leaving bones scattered across landscapes that would soon be buried under advancing dunes. The extinction process wasn't instantaneous. Fossil dating suggests elephants persisted in refugia, isolated areas with more reliable water, for centuries after surrounding regions became uninhabitable. These last populations clung to existence around shrinking lakes and the final perennial springs, but their isolation doomed them. Without genetic exchange between populations and with climate continuing its inexorable shift toward aridity, these remnant herds eventually winked out. The last elephants of the Sahara likely died within the past 5,000 years, shortly before or concurrent with the region's final transformation into desert. Giraffes under African skies. Few images capture the lost world of the Green Sahara more powerfully than the rock art depicting giraffes, graceful, towering figures etched and painted onto cliff faces and cave walls across the desert. These aren't artistic fantasies. They're accurate representations of real animals that browsed acacia trees and shrublands, where today only lifeless rock exists. Giraffe fossils, though rarer than those of some other large mammals, confirm their presence and reveal details about their ecology and eventual disappearance. The giraffes of the ancient Sahara likely belong to species ancestral to or closely related to modern giraffes, though some fossil remains suggest morphological variations. Vertebrae and limb bones recovered from paleontological sites show proportions consistent with modern giraffes, but sometimes with subtle differences in robustness, possibly reflecting adaptations to the Sahara's specific vegetation structure. Some populations may have developed shorter necks or stockier builds in response to available browse heights and the need to survive longer dry seasons, though evidence for this remains fragmentary. Rock art provides the clearest record of giraffe abundance and distribution. Thousands of giraffe images have been catalogued across the Sahara, from Algeria and Libya to Chad and Sudan. The artworks span thousands of years, showing stylistic evolution as different human cultures inhabited the region. Early depictions, dating to the wettest periods around 8,000 to 10,000 years ago, show giraffes in large numbers, often in groups suggesting herds. Later images, from transitional periods when the climate was drying, show fewer giraffes, sometimes depicted alone or in pairs, a possible reflection of declining populations. The precision of these artistic representations is remarkable. Artists captured distinctive giraffe behaviours, browsing on trees with characteristic splayed legs, running with their unique gait, and nursing young. Some paintings show reticulated coat patterns that match modern giraffe subspecies, suggesting the artists observed these animals closely and regularly. Certain sites contain dozens of giraffe figures in single panels, indicating these animals were common enough to dominate the landscape and human consciousness. Giraffes required specific ecological conditions. They're browsers, feeding primarily on leaves, shoots and fruits from trees and tall shrubs, particularly acacias, which were abundant in the Green Sahara's woodland grassland mosaic. Their height allowed them to exploit food sources unreachable by other herbivores, giving them a competitive advantage in ecosystems with diverse vegetation structure. However, this specialization also made them vulnerable. Giraffes need relatively dense woody vegetation, and as the climate dried and trees became sparser, suitable habitat contracted rapidly. The distribution of giraffe fossils and rock art reveals their range during humid periods. They occupied highlands and lowlands, river valleys and open plains, wherever adequate browse existed. Isotopic analysis of fossil teeth suggests giraffes consumed a mix of C3 plants, typical of trees and shrubs, with minimal grass intake, confirming their browsing lifestyle. Seasonal variation in isotopic signatures indicates giraffes moved across landscapes following the phenology of plant growth, exploiting different vegetation zones as wet and dry seasons alternated. Predation-shaped giraffe populations, large carnivores, lions, hyenas, possibly giant extinct predators, hunted giraffes, particularly young and vulnerable individuals. Evidence for this comes indirectly from predator fossils found in the same deposits, and from the ecological logic that such large herbivore populations must have supported substantial carnivore communities. Rock art sometimes depicts hunting scenes, though these more commonly show humans targeting other prey species. The absence of detailed giraffe hunting imagery might suggest these animals were difficult or dangerous to hunt, given their size and powerful kicks. As the Sahara's climate deteriorated, giraffes faced a cascading series of challenges. Vegetation zones shifted southward and upward into shrinking highland refugia. Trees became stunted and widely spaced, reducing food availability. Water sources dried up, forcing giraffes to travel increasing distances between browse areas and drinking sites. Their conspicuous height and advantage in lush woodlands became a liability in increasingly open landscapes where food was scarce and locating water required covering vast distances. The fossil record shows giraffes persisting longer in certain areas than others. Highland regions with more reliable rainfall maintained suitable habitat after lowland plains had already converted to scrub and bare ground. Archaeological and paleontological evidence from these refugia shows giraffes surviving until approximately 5,000 to 4,000 years ago in some locations, contemporary with early North African civilizations. By then, however, they existed only in isolated pockets, remnant populations clinging to the last woodlands, before these too succumbed to advancing aridity. Crocodiles in desert stone. Perhaps no animal better symbolises the green Sahara's watery past than the crocodile, an unambiguous indicator of permanent water, now fossilised in regions where rain hasn't fallen in decades. Crocodile fossils and rock art depicting these apex aquatic predators appear throughout the Sahara, from the mountains of southern Algeria to the dried lake basins of Chad and Sudan. These weren't brief appearances or unusual outliers. Crocodiles were keystone species in the ancient Saharan ecosystem, shaping food webs and community structure for thousands of years before the final desiccation. The crocodile species inhabiting green Sahara waterways were closely related to the Nile crocodile, though some populations may have represented distinct lineages. Fossil remains include skulls, teeth, vertebrae, and osteoderms, the bony plates embedded in crocodile skin. Size estimates based on these fossils suggest individuals regularly exceeded 4 meters in length, with some potentially reaching 5 meters or more. Formidable predators capable of taking down large prey, including mammals at waterholes. Complete or articulated crocodile skeletons are rare, but even isolated bones tell important stories. Osteoderms, which preserve exceptionally well due to their density, are abundant in some fossil deposits, indicating substantial crocodile populations. Tooth marks on mammal bones, including those of extinct antelope, hippos, and other herbivores, show characteristic patterns matching crocodile dentition, confirming these reptiles hunted the same animals depicted in rock art. The distribution of crocodile fossils maps onto ancient hydrological systems. Nearly every major paleolake and river channel has yielded crocodile remains, demonstrating these waterways supported the permanent aquatic environments crocodiles require. Unlike some reptiles that can tolerate temporary water sources, crocodiles need year-round water for thermoregulation, breeding, and hunting. Their presence proves that Saharan lakes and rivers weren't ephemeral puddles, but stable ecosystems persisting for centuries or millennia. Rock art provides extraordinary detail about human-crocodile interactions. Paintings and engravings show crocodiles with anatomically accurate features, ridged backs, powerful tails, distinctive snouts. Some artworks depict crocodiles basking on riverbanks. Others show them swimming or hunting. One famous engraving from the Messac Plateau in Libya shows a crocodile so large it dwarfs nearby human figures, suggesting these reptiles inspired both fear and respect. Humans hunted crocodiles, as evidenced by artistic scenes showing speared crocodiles and archaeological remains of crocodile bones with butchery marks. Crocodile skin and meat would have been valuable resources. However, the danger these animals posed is also documented. Some human skeletons from lakeside settlements show bone trauma consistent with crocodile attacks, reminding us that the Green Sahara's abundance came with significant risks for its human inhabitants. Crocodiles required specific conditions beyond just water. They need basking sites, exposed rocks or sandbars where they can thermoregulate. They need nesting beaches with suitable substrate for egg laying. They need sufficient prey density to support their metabolic needs. The fossil record suggests all these conditions were met throughout the humid period, allowing crocodile populations to thrive across a vast geographic area. Different water bodies supported different population densities. Large, deep lakes with stable fish populations likely hosted the highest crocodile numbers. Smaller, seasonal lakes may have had transient populations that moved between water bodies as conditions changed. River systems would have provided corridors allowing genetic exchange and dispersal, preventing isolated populations from becoming too inbred. This connectivity was crucial for maintaining healthy crocodile metapopulations across the region. As the climate shifted, crocodiles faced existential challenges. Their inability to survive without water meant they couldn't adapt to increasing aridity the way some mammals could. As lakes and rivers dried, crocodile populations became fragmented, isolated in shrinking pools. Fossil evidence shows crocodiles persisted in some refugia long after surrounding areas had become uninhabitable, the last individuals clinging to the final permanent water sources. One particularly poignant fossil site in Chad preserves multiple crocodile skeletons in what was once a lake that dried catastrophically. The bones show no signs of predation or butchery. These animals simply died when their lake evaporated, victims of a climate shift they couldn't escape. Such mass mortality events probably occurred repeatedly as the Green Sahara collapsed, leaving concentrated fossil deposits that now lie beneath meters of wind-blown sand. Hippos beneath the dunes. Few discoveries shock people more than fossilized hippo bones emerging from Saharan sand. Hippos, animals synonymous with sub-Saharan African rivers and wetlands, once wallowed in Saharan lakes and rivers so abundant that multiple hippo species coexisted in the region. Their fossils, rock art depictions, and the ecological implications of their presence reveal just how radically different the Green Sahara was from today's lifeless desert. The primary hippo species in the ancient Sahara was ancestral to, or conspecific with, the modern common hippopotamus. Fossil evidence includes teeth, jaw fragments, limb bones, and occasionally more complete remains. Hippo teeth are particularly diagnostic, with their distinctive shape and wear patterns revealing diet and habitat preferences. Chemical analysis of tooth enamel provides insights into what these animals ate and the water sources they depended on. Fossil sites containing hippo remains are scattered across the Sahara. Some of the richest deposits come from Chad, Niger, and Sudan, regions that once hosted massive lake systems. At Gobero in Niger, paleontologists uncovered a remarkably complete picture of ancient Saharan ecosystems, including numerous hippo fossils alongside those of fish, crocodiles, and humans. The association of these fossils proves these species lived together in functional ecosystems, not as isolated stragglers in marginal environments. Hippos require permanent, deep water. They spend most of each day submerged, emerging at night to graze on shoreline vegetation. This lifestyle demands stable lake or river systems with adequate depth and food resources. The abundance of hippo fossils across the Sahara therefore indicates widespread aquatic habitats meeting these requirements. A landscape of interconnected wetlands supporting populations that may have numbered in the thousands during peak humid periods. Rock art depicting hippos is less common than that showing other large mammals, but where it exists, it's remarkably detailed. Engravings from sites in Libya and Algeria show hippos with characteristic body shapes, including their barrel-like torsos and small ears. Some scenes depict hippos in water, others on land, and several show what appear to be mother-calf pairs, evidence of breeding populations rather than transient individuals. The artistic attention given to hippos suggests they were significant elements of the landscape and human awareness. Hippo ecology shaped Saharan waterways in important ways. Their grazing created and maintained open areas along lake and river margins, preventing woody vegetation from encroaching into aquatic zones. Their trampling and wallowing disturbed sediments, affecting water chemistry and creating microhabitats for invertebrates and fish. Hippo dung, deposited in massive quantities, fertilized aquatic ecosystems, fueling algal blooms that supported food webs benefiting everything from zooplankton to fish to crocodiles. The presence of hippos also tells us about seasonal patterns. Hippos can't survive prolonged dry seasons without refugia, where water persists year-round. Their fossils therefore indicate not just wet climates, but climates with sufficient rainfall consistency to maintain permanent water bodies. Even during the humid period, the Sahara experienced dry seasons, but the combination of deep lakes, groundwater-fed springs, and perennial rivers provided the stability hippos required. Human interactions with hippos are documented in both art and archaeology. Some rock art may depict hunting scenes, though interpreting these images is challenging. Archaeological sites contain hippo bones with butchery marks, proving humans occasionally killed and processed these massive animals. Hippo ivory, from their large canine teeth, was a valuable material, found in burial goods and traded across ancient networks, showing these animals had economic as well as ecological importance. Different hippo populations may have developed distinct characteristics in response to local conditions. Hippos in large, stable lakes face different selective pressures than those in smaller, more variable water bodies. Some populations may have become smaller or larger depending on food availability and competition. Unfortunately, the fossil record isn't complete enough to fully resolve these population-level variations, but subtle differences in fossil morphology hint at this possibility. As the climate deteriorated, hippos faced catastrophic habitat loss. They're among the least adaptable large mammals to drying conditions. Unlike elephants or antelope that can migrate substantial distances, hippos are tied to water both physiologically and behaviourally. As lakes shrank and rivers became seasonal, hippo populations became fragmented and isolated. The spacing between surviving water sources eventually exceeded the distances hippos could travel overland, dooming separated populations to genetic isolation and eventual extinction. The fossil record documents this collapse. Late-stage sites show hippo remains concentrated at the very last permanent water sources, springs and deep lake remnants that persisted after surrounding landscapes had dried. These fossils sometimes show pathological conditions suggesting stressed populations, poor bone density, disease indicators, evidence of malnutrition. The last hippos of the Sahara likely died watching their final pools evaporate, victims of a climate transformation that happened too quickly for evolution to provide solutions. Lions and the mega carnivores. Predators dominated the Green Sahara just as they do modern African savannas, and the fossil and artistic evidence reveals a carnivore guild as diverse and dangerous as any existing today. Lions, large cats, hyenas, and possibly extinct predator species stalked the grasslands and woodlands, forming complex predator-prey relationships that shaped the entire ecosystem. Their presence confirms that the Green Sahara supported prey densities high enough to sustain multiple competing carnivore species, each occupying different ecological niches. Lion fossils from Saharan contexts are rare but documented. Bone fragments and teeth from cave deposits and ancient kill sites prove lions inhabited the region during humid periods. These weren't a different species from modern African lions. Genetic and morphological analysis suggests direct continuity. However, populations isolated in the Sahara during humid intervals may have developed distinct characteristics before disappearing during arid phases or merging with populations elsewhere as habitats shifted. Rock art provides the richest evidence for large carnivores. Lion images appear across the Sahara, from Algeria's Tassili Najjar to Libya's Messac Plateau to Sudan's eastern deserts. Artists depicted lions hunting, resting, and interacting with other species. Some images show extraordinary detail: manes on males, muscular builds, and behavioral postures that match modern lion behavior. The frequency of lion imagery suggests these predators were both common and culturally significant to ancient Saharan peoples. Beyond lions, evidence points to other large cats. Some rock art depicts spotted felids that may represent leopards or an extinct spotted cat species. Leopards are adaptable predators that thrive in varied habitats, and their presence in the Green Sahara would make ecological sense. Fossil remains potentially attributable to leopards include teeth and jaw fragments, though conclusive identification is often difficult with fragmentary specimens. Cheetahs may have also inhabited the region, exploiting open grasslands to hunt fleet-footed prey. Hyenas were important carnivores in the ancient Saharan ecosystem. Fossil evidence for hyenas is stronger than for large cats, with numerous teeth, jaw fragments, and postcranial bones recovered from cave deposits and Paleolake sediments. Hyenas aren't just scavengers, they're effective hunters capable of taking down prey as large as wildebeest. In the Green Sahara, hyenas would have competed with and scavenged from lions and other predators, playing crucial roles in nutrient cycling and carcass processing. Some fossils hint at even more exotic carnivores. Fragmentary remains suggest that extinct predator species, possibly oversized hyenas or cat relatives unknown from modern faunas, may have existed in the ancient Sahara. These interpretations remain tentative, requiring more complete fossils for confirmation. However, the diversity of herbivores documented in the Green Sahara would have supported diverse predator guilds, making the presence of unusual carnivore species plausible. Predator behavior shaped the landscape in measurable ways. Prey species developed anti-predator strategies, herding behaviors, vigilance patterns, habitat selection favoring areas with visibility or escape routes. Predators influence where herbivores grazed and browsed, creating spatial patterns in vegetation use. Kill sites concentrated nutrients in specific locations, creating hotspots that benefited scavengers, decomposers, and ultimately plant growth. This web of interactions generated the complex ecological dynamics characteristic of productive predator-prey systems. Human hunters competed with animal predators for game. Archaeological evidence shows humans successfully hunted large mammals using projectile weapons, traps, and coordinated group tactics. This competition may have created conflict. Rock art possibly depicts confrontations between humans and lions or hyenas, though interpretations vary. Some skeletal remains from ancient human burials show bone trauma consistent with large carnivore attacks, confirming that predators occasionally preyed on humans. Carnivore populations responded dynamically to prey availability. During periods when rainfall was most consistent and prey populations highest, carnivore numbers would have increased. During drier intervals within the overall humid period, predator populations probably declined or shifted geographically, tracking prey movements. This flexibility allowed carnivores to persist through environmental fluctuations, but only up to a point. Once the climate shift became too severe, even the most adaptable predators faced extinction or forced migration. As the Green Sahara dried, carnivores faced a cascading crisis. Prey populations declined first, fragmenting and decreasing in density. Predators, being fewer in number and requiring larger territories, felt this impact immediately. Competition intensified as remaining prey became concentrated around shrinking water sources. Lions and other large carnivores require substantial ranges and regular kills to survive. As those conditions disappeared, so did the predators. The last large carnivores of the Sahara likely existed in isolated refugia until approximately 4,000 to 5,000 years ago. They may have persisted in highland areas where prey remained more abundant, or near the final permanent water sources where herbivores concentrated. Eventually, however, those refugia also failed. The lions, hyenas, and other carnivores either died out or migrated south into the Sahel and sub-Saharan regions, merging with populations that still had viable habitats. The Saharan populations, adapted over generations to local conditions, effectively vanished, their genetic distinctiveness lost as the desert advanced. The addax and desert antelope. Among the most specialized inhabitants of the Green Sahara were the desert-adapted antelope, species that evolved to cope with seasonal aridity even during humid periods, and whose descendants include some of the world's rarest large mammals. The addax, scimitar-horned oryx, and dama gazelle represent evolutionary lineages shaped by the Sahara's oscillating climate, their adaptations reflecting thousands of generations responding to environments that swung between abundant and harsh. The addax is perhaps the ultimate desert antelope, superbly adapted to extreme aridity. Fossil evidence and rock art show addax inhabited the Green Sahara, though they likely occupied different niches than during dry periods. Addax possess specialized physiologies. They can survive without drinking water, obtaining all necessary moisture from vegetation. Their broad hooves prevent sinking in sand. Their pale coloration reflects heat. These adaptations didn't evolve during humid periods, but were maintained through them, allowing addax to exploit marginal habitats even when the region overall was productive. Rock art depicts addax with their characteristic spiral horns and stocky builds. Images show them in groups, suggesting herd behavior consistent with modern observations. Artistic representations span the entire humid period and beyond, proving addax persisted through climatic transitions that eliminated less adapted species. Their ability to survive extreme conditions, both abundance and scarcity, made them evolutionary success stories, though modern populations are critically endangered, victims of overhunting rather than climate change. The scimitar-horned oryx once ranged across the Sahara and Sahel. These striking antelope, with their backward curving horns and white coats, appear frequently in rock art. Fossil remains include horns, skull fragments, and postcranial bones from sites across the Sahara. Like addax, oryx evolved extreme desert adaptations, but thrived during humid periods by exploiting seasonal movements between different vegetation zones. Their migrations took them hundreds of kilometers following rainfall, a strategy that worked as long as the overall climate regime supported vegetation growth. Isotopic analysis of oryx fossils reveals dietary flexibility. During wet seasons, oryx consumed fresh grasses and forbs. During dry periods, they switched to browse, leaves, shoots, and even plant parts with high water content, like succulent herbs. This dietary plasticity, combined with physiological water conservation, allowed oryx to inhabit landscapes that were transitional or variable, giving them resilience through climatic fluctuations. Dama gazelles, the largest gazelle species, also inhabited the ancient Sahara. These elegant animals appear in rock art across the region, often depicted in running poses that capture their speed and grace. Dama gazelles occupy an ecological middle ground between true desert specialists like addax and savanna species, requiring more consistent moisture. Their presence in the Green Sahara indicates habitat mosaics, where open grasslands, shrublands, and wooded zones created diverse niches. Beyond these species, the Green Sahara likely hosted other antelope forms, some now extinct, others persisting in reduced ranges outside the desert. Fossil assemblages include horns and teeth that don't match modern species precisely, hinting at extinct lineages or populations with unique characteristics. The challenge of identifying fragmentary fossils means the true diversity of ancient Saharan antelope may never be fully known, but clearly it exceeded what exists today. Antelope ecology influenced the broader ecosystem. As primary consumers, they converted plant biomass into animal protein, supporting carnivore populations. Their grazing and browsing affected vegetation structure, maintaining open grasslands and preventing woody encroachment in some areas while creating browse lines in others. Their migration spread seeds and nutrients across landscapes, connecting distant parts of the ecosystem through their movements. Human hunters targeted antelope extensively. Archaeological sites contain abundant antelope bones, showing these animals were dietary staples. Rock art frequently depicts hunting scenes with antelope as prey, using techniques ranging from individual stalking to communal drives. The ease of hunting certain antelope species may have contributed to population declines even before climate change became the primary threat, though distinguishing human impacts from environmental drivers remains challenging. As the Sahara dried, desert-adapted antelope initially expanded their ranges, moving into areas becoming more arid. This seemingly paradoxical response occurred because competition decreased. Less drought-tolerant species disappeared, leaving resources for specialists. However, this advantage was temporary. Once aridity crossed critical thresholds where even drought-adapted vegetation became too sparse, even specialists like addax and oryx faced crises. The fossil record shows antelope persisting in the Sahara later than most large mammals. Even as elephants, giraffes, and hippos vanished, antelope remained in suitable patches. Eventually, though, their populations became too fragmented to maintain genetic diversity or recover from local extinctions. Some populations survived by migrating to the Sahel, where they persist in critically small numbers today. Others simply died out, leaving only fossils and rock art as evidence they once thrived in numbers impossible to imagine now. The Barbary sheep and mountain dwellers. While much attention focuses on lowland species, the highlands and mountainous regions of the ancient Sahara hosted their own unique fauna, adapted to cooler temperatures, rocky terrain, and the ecological dynamics of elevation gradients. The Barbary sheep, also called aoudad, represents one of these montane specialists, a species that survived the Sahara's desiccation by retreating into highland refugia, where conditions remained marginally tolerable even as surrounding lowlands became uninhabitable. Barbary sheep aren't true sheep, but members of a unique caprine lineage that evolved in North African mountains. During the humid period, their range likely extended across suitable highland and escarpment habitats throughout the Sahara. Rock art depicts them with characteristic features: powerful builds, thick necks, long hair on the throat and forelegs, and curved horns. These images appear in mountainous regions where Barbary sheep still survive today, suggesting long-term continuity in these refugial habitats. Fossil evidence for Barbary sheep in Saharan contexts is limited, partly because highland environments have poorer fossil preservation than lakebeds and caves. However, bones and horn cores attributed to Barbary sheep appear in archaeological contexts, proving humans hunted them. Isotopic analysis of these remains shows diets dominated by browse, shrubs, herbs and grasses typical of mountain vegetation, confirming their habitat preferences have remained stable across millennia. The highlands hosting Barbary sheep created distinct microclimates. Even during humid periods, mountains remained cooler and often drier than lowlands, because they rose above moisture-bearing air masses. This created vegetation zones with unique compositions: drought-adapted shrubs, endemic herbs, and grasses that could tolerate rocky soils and seasonal water stress. Barbary sheep evolved to exploit these resources, developing digestive capabilities to process tough, low-nutrition vegetation. Other mountain-adapted species shared these habitats. Rock art suggests the presence of ibex or ibex-like caprines in some highland areas. While definitive fossils are scarce, imagery showing agile, climbing ungulates on steep terrain hints at species adapted specifically to vertical landscapes. These animals would have occupied different niches than Barbary sheep, perhaps preferring more precipitous cliffs or exploiting different vegetation zones. Birds of prey and other avian species used highland areas as nesting sites and hunting grounds. While direct fossil evidence for birds is minimal, bird bones preserve poorly. Rock art depicts eagles, vultures and other large birds. These species would have played important ecological roles, predating small mammals, scavenging carcasses and dispersing seeds. Highland environments, with their thermal updrafts and visibility, provided ideal conditions for soaring birds. Humans exploited mountain resources extensively. Highland caves and rock shelters contain archaeological deposits showing repeated occupation over thousands of years. These sites were strategic refugia during environmental downturns, offering reliable water sources from springs, diverse game animals, and protection from both weather and human competitors. The rock art concentrated in these locations documents the species people encountered and hunted, with Barbary sheep featuring prominently. Mountains served as critical refugia during climatic transitions. When lowlands dried, many species retreated upslope following their required habitats. This created compression zones where species from different elevations crowded into shrinking suitable areas. Competition intensified, but for species already adapted to mountain conditions like Barbary sheep, these periods represented opportunities to expand within montane environments even as their total geographic range contracted. The survival strategy that worked for Barbary sheep failed for most other large mammals. Mountains provided isolated habitat patches, but they couldn't support the space requirements of elephants, the water needs of hippos, or the prey densities required by large carnivores. Only species with modest spatial needs, physiological tolerance for aridity, and ability to exploit low productivity vegetation could persist. Barbary sheep met these criteria. Most Saharan megafauna did not. Modern Barbary sheep populations represent relic distributions, isolated remnants of once continuous ranges. Genetic studies show these populations are highly fragmented, with limited gene flow between mountain ranges now separated by uninhabitable desert. This fragmentation began when lowland corridors dried out, stranding highland populations. Over subsequent millennia, these isolated groups diverged slightly, though not enough to constitute separate species. Their persistence demonstrates both remarkable resilience and the precariousness of survival in marginal habitats. Ostriches and giant birds. The Green Sahara hosted an impressive diversity of large, flightless and flying birds, species that exploited the region's varied habitats from open grasslands to wetland margins. Ostriches, the world's largest living birds, were prominent members of this avian community, their fossils and rock art depictions revealing populations that thrived across the ancient Saharan landscape before being pushed south as desertification advanced. Ostrich fossils from Saharan contexts include eggshell fragments, bones, and occasionally more complete remains. Eggshells are particularly abundant and informative. Their thickness, pore structure, and isotopic composition reveal environmental conditions and ostrich physiology. Ancient Saharan ostrich eggshells show characteristics matching modern ostriches, confirming species continuity. However, some specimens hint at population-level variation, possibly reflecting adaptations to local conditions. Rock art depicting ostriches appears throughout the Sahara, spanning the entire humid period. Artists rendered ostriches with recognizable features: long necks, powerful legs, distinctive feather patterns. Some images show ostrich eggs, which were valuable resources for humans. The shells served as water containers after contents were consumed, and decorative items made from engraved ostrich eggshells appear in archaeological contexts across North Africa and beyond, demonstrating trade networks extending thousands of kilometres. Ostriches occupied open habitats where their running ability, up to 70 kilometres per hour, gave them advantages in escaping predators. Their omnivorous diet allowed them to exploit diverse food sources: grasses, seeds, leaves, insects, and small vertebrates. This dietary flexibility meant ostriches could persist through seasonal changes and environmental fluctuations that challenge more specialised species. They required water more frequently than some desert-adapted mammals, but could survive moderate dry periods by metabolising water from food. Beyond ostriches, evidence suggests other large birds inhabited the Green Sahara. Bustards, large terrestrial birds capable of flight, likely occurred in grassland habitats. While direct fossils are rare, ecological principles suggest these birds would have found suitable conditions in the ancient Saharan savannas. Rock art possibly depicting bustards or similar large birds supports this interpretation, though identifying species from artistic representations alone is speculative. Waterfowl diversity was probably high, given the abundance of lakes and rivers. Fossil sites near ancient water bodies contain bird bones tentatively identified as ducks, geese, and other aquatic species. These birds would have migrated through or resided in the Sahara, exploiting rich aquatic resources for breeding and feeding. The presence of fish-eating birds is confirmed by occasional finds of bird remains in contexts suggesting piscivorous diets. Raptors, eagles, hawks and vultures occupied predator niches in the avian community. Rock art depicts large birds of prey, sometimes in scenes suggesting interactions with mammals. Large vultures would have been crucial scavengers, consuming carcasses left by mammalian carnivores and returning nutrients to the ecosystem. Fossil evidence for these birds is minimal, but their ecological necessity in systems with abundant large mammals makes their presence certain. Flamingos may have inhabited some Saharan lakes. Modern flamingos occur in saline lakes across Africa, and the ancient Sahara included lakes with varying salinity, some freshwater, others brackish or saline, depending on evaporation rates and water sources. Flamingo fossils from North African sites slightly outside the Sahara proper suggest these specialised filter feeders exploited Saharan wetlands when conditions suited their needs. The impact of birds on the ecosystem extended beyond their obvious ecological roles. Birds disperse seeds across vast distances, connecting vegetation communities and facilitating plant migration as climate zones shifted. Predatory birds controlled rodent and insect populations. Waterfowl concentrate nutrients in wetlands through their droppings, enhancing aquatic productivity. The loss of avian diversity when the Sahara dried impoverished the ecosystem in ways often overlooked in discussions focused on charismatic megafauna. Ostriches faced mounting challenges as aridity increased. Their water requirements, though modest compared to mammals like hippos, became limiting as surface water disappeared. Their food sources shifted from diverse grasslands to scattered desert scrub, reducing nutritional quality and availability. Predation pressure may have intensified if ostriches became concentrated around remaining water sources where carnivores hunted. Unlike flying birds that could migrate long distances quickly, ostriches had to walk, making escaping deteriorating conditions more difficult. The fossil record shows ostriches persisting in the Sahara later than many mammal species, but eventually they too retreated. Modern ostriches occur in the Sahel and savannas south of the Sahara, their northern range limit roughly corresponding to where rainfall becomes insufficient to support their needs. The genetic heritage of Saharan ostrich populations likely persists in these modern birds, though distinguishing this ancestry requires detailed genomic analysis not yet conducted. The ostriches of today thus carry within them the evolutionary history of the Green Sahara's vanished grasslands. Snakes, lizards, and desert dragons. The reptile fauna of the Green Sahara remains less well documented than its mammals, but fragmentary evidence reveals a diverse herpetofauna that exploited the region's varied habitats. Snakes, lizards, and other reptiles thrived in environments ranging from lake margins to rocky uplands, their ectothermic physiology allowing them to survive conditions that challenge warm-blooded animals. As the Sahara dried, many reptile species adapted rather than disappeared, becoming the desert specialists that inhabit the region today. Fossil evidence for Saharan reptiles is challenging to interpret because reptile bones are small, fragile, and often overlooked in excavations focused on large mammals. However, snake vertebrae and lizard jaw elements appear in cave deposits and archaeological sites. These fossils represent species adapted to the savanna woodland environments of the humid period, some matching modern North African reptiles, others suggesting extinct or displaced lineages. Monitor lizards likely inhabited the Green Sahara. Modern Nile monitors occur throughout sub-Saharan Africa in diverse habitats, and their ecological flexibility would have suited them to ancient Saharan conditions. Large monitor lizards leave distinctive traces, shed teeth, claw marks, and scat, though identifying these signs in the fossil record is difficult. Rock art possibly depicting large lizards supports their presence, though artistic interpretations of reptiles tend to be less detailed than mammal depictions. Venomous snakes certainly occurred in the ancient Sahara. Vipers adapted to arid conditions today inhabit Saharan margins, and their ancestors likely range more widely during humid periods. Cobra fossils from North African sites demonstrate that elapid snakes have long histories in the region. These snakes would have preyed on rodents, birds, and other small vertebrates, playing important roles in controlling prey populations and serving as food for larger predators. Python fossils from sites near the current Saharan margins hint that these large constrictors may have extended into the Green Sahara during humid peaks. Pythons require consistent prey populations, usually mammals and birds, and adequate cover for ambush hunting. The dense vegetation along ancient Saharan rivers and around lakes could have supported pythons, though they probably occurred at low densities compared to mammals or smaller reptiles. Chameleons and other arboreal lizards inhabited wooded areas. While direct fossil evidence is lacking, the ecological logic is compelling. The acacia woodlands and gallery forests of the Green Sahara would have provided ideal habitat for species exploiting three-dimensional vegetation structure. Modern North African chameleons, though now restricted to more mesic areas, likely had broader ranges when the Sahara was green. Turtles and tortoises represent an important component of the ancient fauna. Freshwater turtle fossils appear in lake deposits alongside fish and crocodile remains. These turtles exploited aquatic resources, feeding on vegetation, invertebrates, and carrion. Tortoise remains from drier contexts suggest these reptiles inhabited grasslands and scrublands, where their ability to tolerate water scarcity gave them advantages. Tortoises served as prey for large carnivores and humans, their shells appearing in archaeological contexts. Amphibians, though not reptiles, shared habitats with reptiles and faced similar challenges. Frog and toad fossils from Saharan wetlands prove these moisture-dependent animals thrived during humid periods. Their calls would have filled the night air around ancient lakes, and their tadpoles filled shallow waters. As wetlands dried, amphibian populations crashed, surviving only in the most persistent water sources or disappearing entirely from the region. The transition from Green Sahara to desert actually benefited some reptile lineages. Species pre-adapted to aridity through efficient water conservation, heat tolerance, and ability to exploit sparse resources found expanding niches as competition from moisture-dependent species declined. Lizards capable of surviving on scattered insects and seeds thrived as the environment shifted toward conditions favouring ectotherms over endotherms. Modern Saharan herpetofauna represents a filtered subset of the Green Sahara's reptile diversity. Species requiring permanent water or dense vegetation disappeared or retreated southward. Desert specialists expanded. Some lineages evolved enhanced adaptations to extreme aridity, sand swimming behaviours, nocturnal activity patterns, metabolic water production. The Sahara's current reptile community thus reflects both evolutionary heritage from the Green Sahara and subsequent adaptation to desert conditions. The continuity of reptile lineages through the Saharan climate transition contrasts with the megafaunal extinctions that characterize the period. While elephants, hippos, and most large mammals couldn't adapt fast enough, reptiles with their lower metabolic demands, smaller space requirements, and physiological flexibility navigated the transformation. This differential survival reshaped the ecosystem fundamentally, from one dominated by large-bodied endotherms to one where ectothermic reptiles became proportionally more important. A shift recorded in the bones beneath the sand. Fish in fossil lakes. The aquatic ecosystems of the Green Sahara supported extraordinary fish diversity, rivaling modern African Rift Valley lakes in species richness and ecological complexity. These fish populations sustained the crocodiles, birds, and humans that depended on Saharan wetlands, and their fossils provide crucial evidence for reconstructing ancient hydrological systems and water chemistry. The disappearance of Saharan fish as lakes dried represents one of the most complete aquatic extinctions documented in the fossil record. Fossil fish from Saharan paleo lakes include species familiar from modern Nile and African lake systems. Tilapia fossils are abundant, their distinctive teeth and skull morphology making them easily identifiable. These teak-leered fish thrive in warm, productive waters and can tolerate variable conditions, explaining their success in ancient Saharan lakes. Multiple tilapia species likely coexisted, partitioning resources through differences in feeding strategies. Some grazing algae, others eating invertebrates, still others consuming detritus. Catfish fossils represent another major component of the ancient fish fauna. Saharan deposits yield remains of clariid catfish, air-breathing species that can survive temporary water loss by breathing atmospheric oxygen and even travelling short distances overland. This adaptation would have been crucial in ecosystems subject to seasonal fluctuations. Larger catfish species, potentially including relatives of Nile catfish, likely served as apex aquatic predators in systems where crocodiles weren't abundant. Lungfish fossils provide dramatic evidence for the challenges ancient fish faced. Lungfish can survive droughts by living in mud burrows, breathing air, while waiting for rains to return. Fossil lungfish burrows, preserved in ancient lake sediments, show these fish use this strategy in the Green Sahara, just as modern African lungfish do today. The presence of lungfish indicates lakes experience seasonal or periodic drying, even during overall humid conditions, requiring adaptations for survival. Characins, relatives of South American piranhas, may have inhabited Green Saharan waters. While direct fossil evidence is debated, some fish remain show characteristics suggesting character affinities. These fish are primarily African in distribution today, with diverse species in sub-Saharan lakes and rivers. Their presence in the ancient Sahara would indicate connections between Saharan and sub-Saharan freshwater systems during humid periods, allowing fish to disperse between regions. Fossil evidence reveals details about fish body sizes and age structures that inform understanding of ancient lake ecology. Growth rings in fish otoliths, ear bones, record seasonal patterns and individual lifespans. Analysis of Saharan fish otoliths shows some lakes supported long-lived fish populations with multiple age classes, indicating stable conditions persisting for decades. Other sites show truncated age structures suggesting population crashes or rapid environmental changes. Chemical analysis of fish fossils provides insights into ancient water conditions. Isotopic signatures in fish bones and scales reflect the chemistry of the water they lived in, which in turn reflects rainfall, evaporation rates, and watershed geology. Studies of Saharan fish fossils reveal that different lakes had distinct chemistries, some freshwater, others slightly saline, some with seasonal variation in composition. This chemical diversity supported different fish communities adapted to local conditions. Fish served as crucial dietary resources for humans and other predators. Archaeological sites near ancient lakes contain abundant fish bones, scales and processing tools, bone harpoons, net weights and fish hooks. These finds prove fishing was a primary subsistence activity for lakeside communities. The species composition in archaeological fish assemblages changes over time, tracking ecological shifts as lake conditions varied. During optimal periods, diverse fish species appear. During stressful periods, only hardy, tolerant species persist. As the Sahara dried, fish populations faced cascading crises. Lakes shrank, concentrating fish in smaller volumes with deteriorating water quality. Increased salinity from evaporation stressed freshwater species. Oxygen levels declined as warm, stagnant water couldn't maintain dissolved oxygen concentrations. Temperature extremes increased as water bodies became shallower. These stresses operated synergistically, pushing fish populations toward collapse. The fossil record documents mass mortality events where entire fish populations died as lakes evaporated. These deposits contain thousands of fish skeletons in concentrated layers, sometimes with individuals showing stress indicators, deformed bones, disease markers, stunted growth. Such catastrophic mortality represents the final stages of lake systems, when conditions deteriorated too rapidly for fish to adapt or escape. These mass death assemblages became time capsules, preserving snapshots of ecosystem collapse. Some fish populations survived longer than expected by exploiting refugia, deep spring-fed pools, or lake remnants where water persisted after surrounding areas dried. Genetic studies of modern North African fish suggest some lineages descended from populations that survived in these refugia before being reconnected during subsequent humid periods or expanding from Saharan margins. However, most ancient Saharan fish populations left no modern descendants, their lineages ending when the last waters dried. The Saharan Stone Age humans. Humans weren't just observers of the Green Sahara, they were active participants in its ecosystems, hunters, gatherers, artists, and eventually herders who shaped landscapes and were shaped by them. The archaeological record reveals sophisticated Stone Age cultures that thrived in the abundant Saharan environments before being forced to adapt, migrate, or perish when desertification destroyed their way of life. The rock art they left behind documents their world with extraordinary clarity, preserving images of animals, people, and activities that would otherwise be lost. The earliest humans in the Green Sahara were hunter-gatherers exploiting its rich resources. Sites dating to the early Holocene reveal communities living along lake shores, subsisting on fish, aquatic mammals, birds, and terrestrial game. Stone tool assemblages show sophisticated microlith technology, tiny, precisely crafted stone blades hafted into bone or wood shafts to create composite hunting weapons. These tools allowed efficient hunting of diverse prey species, from small gazelles to large dangerous game. Bone harpoons recovered from lakeside sites demonstrate specialized fishing technology. These barbed points carved from animal bones were attached to lines and thrown or thrust into fish and aquatic mammals. Their design shows remarkable sophistication, with barbs angled to prevent prey from escaping and holes for line attachment positioned to maximize effectiveness. The abundance of fish bones at sites with harpoons proves these tools were highly successful, allowing humans to exploit aquatic resources intensively. Pottery appears in the Saharan archaeological record remarkably early, by 10,000 years ago, making it among the oldest pottery in the world. Early Saharan ceramics show diverse forms and decorations, with wavy line motifs being particularly characteristic. These vessels allowed storage of food and water, processing of aquatic resources, and possibly fermentation of plant materials. The appearance of pottery correlates with increasingly sedentary lifestyles tied to reliable aquatic resources, marking a shift toward more complex societies. Rock art represents the most visible legacy of green Saharan peoples. Thousands of sites across the desert preserve paintings and engravings spanning millennia. The oldest images, dating to the wettest periods, depict wild animals, elephants, giraffes, hippos, crocodiles, alongside human figures engaged in hunting. These artworks show naturalistic styles capturing anatomical details and behaviours with remarkable accuracy. Artists use pigments derived from minerals, ochres for reds and yellows, manganese oxides for blacks, mixed with binding agents and applied with fingers, brushes, or by blowing through tubes. The subject matter of rock art evolved over time, tracking environmental and cultural changes. Early art focuses on wild animals and hunting. Later images show domesticated cattle appearing around 7,000 years ago, marking the arrival of pastoralism in the Sahara. These pastoral period artworks depict herds of cattle, milking scenes, and elaborate ceremonies involving livestock. The artistic style also changed, becoming more stylized and abstract, possibly reflecting different cultural groups or changing artistic traditions. Human impact on the green Saharan ecosystem intensified with pastoralism. Cattle, sheep, and goats transformed landscapes through grazing and trampling. Herders burned vegetation to promote fresh growth, altering plant communities. Concentrated herds around water sources degraded vegetation and accelerated erosion. Some researchers argue that pastoral activities contributed to Saharan desertification by removing vegetation cover and destabilizing soils, making the landscape more vulnerable when rainfall declined. However, separating human impacts from climatic drivers remains challenging. Social complexity increased during the pastoral period. Cemetery sites reveal social differentiation, with some individuals buried with elaborate grave goods, while others had simple interments. This suggests hierarchical societies developed, possibly with wealthy herders controlling large cattle herds and resources. Conflict may have increased as populations grew and resources became contested. Some skeletal remains show evidence of violent trauma. Trade networks connected Saharan communities with distant regions. Shells from the Mediterranean and Red Sea appear in Saharan archaeological sites, sometimes thousands of kilometers from their sources. These shells served as ornaments and possibly as trade goods or currency. Stone materials for tool making also moved along trade routes, with high-quality flint from specific sources appearing far from outcrops. These networks demonstrate that green Saharan peoples were not isolated, but connected to broader networks spanning North Africa and beyond. As desertification progressed, human communities faced impossible choices. Archaeological evidence shows settlements abandoning lakeside locations as waters dried. Populations fragmented, some migrating south toward the Sahel, others moving north toward Mediterranean climates, still others attempting to persist in shrinking refugia around the last reliable water sources. Some groups successfully transitioned to full nomadic pastoralism, developing strategies to exploit marginal environments. Others failed to adapt, their abandoned settlements and graves marking places where communities ended. The final centuries of human occupation in the Central Sahara show cultural stress. Tool quality declined. Settlements became temporary camps rather than substantial villages. Skeletal remains show increased evidence of nutritional stress and disease. Rock art from this period sometimes depicts conflict and appears more desperate in tone, with images of armed confrontations and emaciated animals. By around 4,000 years ago, most of the Sahara had been abandoned, with humans persisting only in marginal areas or oases. Modern Saharan peoples, Tuareg, Tubu and others, likely descend partly from green Saharan populations that adapted to desert conditions. Genetic studies show these groups carry ancient African lineages predating desertification, suggesting continuity despite dramatic environmental change. Their traditional knowledge of desert survival, finding water, navigating featureless landscapes, utilizing sparse resources, may represent cultural adaptations developed as the Sahara dried. In this sense, the people of the Green Sahara never completely vanished, but transformed along with their environment. Monsoon mechanics and orbital forcing. The transformation of the Sahara from verdant landscape to barren desert wasn't random. It resulted from predictable changes in Earth's orbital mechanics that altered how much solar energy reached different parts of the planet at different seasons. Understanding these orbital forcing mechanisms is crucial for explaining not just the Green Sahara, but similar climate oscillations throughout Earth's history. The mathematical precision of these astronomical cycles, first recognized by Milutin Milankovitch, explains why the Sahara has greened and dried repeatedly over the past several million years. Earth's orbit around the Sun isn't perfectly circular or stable. It varies in three main ways, each operating on different timescales. First, orbital eccentricity. How elliptical the orbit is changes on roughly 100,000-year cycles. When eccentricity is high, Earth's distance from the Sun varies significantly between its closest approach and farthest point. When eccentricity is low, the orbit is nearly circular and distance variation is minimal. This affects total annual solar energy received and seasonal contrasts. Second, axial tilt. The angle at which Earth's rotation axis tilts relative to its orbital plane varies between about 22 and 25 degrees on a 41,000-year cycle. Greater tilt means more extreme seasons, with higher latitude regions receiving more summer sunlight and less winter sunlight. Lower tilt reduces seasonal contrasts. This cycle affects the strength of seasonal heating differences that drive atmospheric circulation patterns, including monsoons. Third, precession, the slow wobble of Earth's rotation axis, operates on roughly 23,000-year cycles. Precession determines which hemisphere experiences summer when Earth is closest to the Sun versus farthest away. Currently, Northern Hemisphere summer occurs when Earth is farthest from the Sun, moderating northern summers. When precession shifts this alignment, northern summers become more intense, strengthening monsoon systems that depend on strong seasonal heating contrasts. These three cycles interact to create complex patterns of solar energy distribution. The most important configuration for the Green Sahara occurs when Northern Hemisphere summer coincides with Earth's closest approach to the Sun, when axial tilt is relatively high, and when eccentricity amplifies the effect. This combination maximizes summer solar heating in northern Africa, intensifying the temperature contrast between land and ocean that drives monsoon winds. Modern monsoon systems develop because land heats faster than ocean in summer, creating low pressure over continents that draws in moist ocean air. In northern Africa today, this effect is relatively weak, producing monsoons that reach only to the Sahel, leaving the Sahara arid. But when orbital mechanics amplified summer heating 10,000 years ago, the temperature contrast intensified dramatically. Atmospheric low pressure over northern Africa strengthened, pulling monsoon winds far northward, hundreds of kilometers beyond their modern limits. Climate models simulating these orbital configurations reproduce the Green Sahara remarkably well. When researchers input past orbital parameters into global climate models, the simulations predict increased rainfall across the Sahara, greening of vegetation, and expansion of lakes, matching geological evidence precisely. This validation demonstrates that orbital forcing alone, without invoking other mechanisms, sufficiently explains Saharan humid periods. The physics is straightforward. Change solar energy distribution, change temperature patterns, change atmospheric circulation, change precipitation. But the story includes complicating factors. Vegetation itself amplifies the effect through biogeophysical feedback. When monsoons bring rain and vegetation spreads, the darker, rougher vegetated surface absorbs more solar energy and increases evapotranspiration, plants releasing water vapor, which further moistens the atmosphere and enhances rainfall. This positive feedback makes the transition to humid conditions more dramatic once a threshold is crossed. Conversely, when vegetation dies during drying transitions, bare soil and sand reflect more sunlight and provide less moisture, accelerating aridification. Lake expansion created additional feedback. Large water bodies affect local climate by moderating temperature, increasing humidity, and altering atmospheric circulation. When Saharan lakes were extensive, they enhanced rainfall in surrounding areas through evaporative moisture recycling. As lakes shrank, this effect diminished, further reducing rainfall. These feedbacks meant the Sahara wasn't simply responding passively to orbital forcing, but actively amplifying transitions between states. Evidence for multiple humid periods throughout the Pleistocene comes from marine sediment cores off the African coast. These cores contain layers of terrestrial sediments and organic material washed into the ocean from Saharan rivers during humid periods, alternating with wind-blown dust from desert periods. The timing of these layers matches orbital cycles predicted by Milankovitch theory, providing strong evidence that orbital forcing repeatedly transformed the Sahara over hundreds of thousands of years. The most recent transition from humid to arid conditions began around 6,000 to 5,000 years ago. Orbital parameters shifted unfavorably. Northern Hemisphere summer moved away from perihelion, reducing seasonal heating contrast. Monsoons weakened. Rainfall declined. Vegetation died back, triggering feedback processes that accelerated drying. The transformation wasn't instantaneous. It occurred over centuries to millennia. But on human timescales, it was catastrophic, fundamentally altering the environment within spans shorter than individual lifetimes. This understanding has profound implications. The current arid Sahara is temporary on geological timescales. Future orbital configurations will eventually bring conditions favouring monsoon intensification and Saharan greening again, though this won't occur for tens of thousands of years. Conversely, the orbital cycles that greened the Sahara in the past are still operating, meaning that without human-caused climate change, natural processes would eventually return the region to more humid conditions. How anthropogenic climate change will interact with these natural cycles remains uncertain, adding another layer of complexity to predicting the Sahara's future. The speed of collapse. One of the most startling discoveries about the Green Sahara's demise is how rapidly it occurred. Early studies assumed the transition from humid to arid conditions was gradual, unfolding over millennia as orbital parameters slowly changed. However, high-resolution paleoclimate records reveal a dramatically different story. The collapse was abrupt, occurring in centuries or even decades, fast enough that humans and animals would have experienced catastrophic environmental changes within single lifetimes. This rapid transformation challenges assumptions about how ecosystems respond to climate forcing and raises urgent questions about abrupt transitions in Earth's climate system. The evidence for rapid collapse comes from precisely dated sediment cores extracted from ancient Saharan lake beds. These cores preserve layered records, where each thin band represents a year or season of deposition. Analysis shows periods where lake sediments abruptly transition to wind-blown dust, indicating lakes dried out completely in very short intervals. Radiocarbon dates bracketing these transitions constrain their timing, revealing transformations that occurred in 50 to 200 years. Geological instance. One well-studied example comes from Lake Yoa in northeastern Chad, one of the few permanent Saharan lakes today. Sediment cores show this lake nearly dried out around 5,000 years ago, but subsequently recovered slightly due to groundwater inputs. The initial drying phase, when lake level dropped catastrophically, occurred over approximately 100 years. For a lake system that had existed continuously for thousands of years, this represents an essentially instantaneous death with implications cascading through the entire ecosystem. Pollen records from lake cores show equally abrupt vegetation changes. Within the resolution of dating methods, typically decades to a century, vegetation assemblages shift from diverse grassland woodland communities to impoverished desert scrub. Trees disappear from pollen records suddenly, replaced by drought-tolerant grasses, and eventually by almost nothing. These transitions don't show gradual species-by-species replacements, but wholesale community collapses, suggesting thresholds were crossed beyond which ecosystems couldn't maintain themselves. What causes such rapid transitions? The answer involves feedback mechanisms that create threshold effects. As rainfall declines, vegetation thins, reducing evapotranspiration and moisture recycling. This causes further rainfall declines, killing more vegetation, a positive feedback that accelerates once initiated. Similarly, as vegetation dies, bare soil reflects more sunlight and heats up, altering local atmospheric circulation in ways that reduce rainfall. These feedbacks create tipping points where gradual forcing produces sudden responses. Dust records from ocean sediment cores show dramatic increases in Saharan dust deposition around 5,000 years ago, marking the transition to desert conditions. Dust flux increased by factors of 5 to 10 within centuries, indicating vast new areas of exposed soil vulnerable to wind erosion. This dust wasn't just a symptom of desertification, but potentially a contributor. Airborne dust can affect atmospheric radiation balance and cloud formation, possibly further suppressing rainfall in source regions. Archaeological evidence documents human responses to rapid environmental deterioration. Settlement patterns show clusters of sites dating to the late humid period suddenly abandoned, with no evidence of gradual population decline, but rather wholesale abandonment over short periods. Cemetery sites show burial practices truncated. Communities that had used specific burial grounds for generations simply stopped, suggesting populations dispersed or died out. The rock art record shows similar patterns, with pastoral imagery abruptly giving way to more arid-adapted subjects or ceasing entirely in many regions. Animal fossils provide heartbreaking evidence for rapid ecosystem collapse. Mass mortality deposits containing dozens to hundreds of individuals from single species represent catastrophic die-offs when critical resources fail. These weren't predation events or disease outbreaks, but environmental deaths, entire populations perishing when water sources or food supplies disappeared. The fact that these mortality events are preserved in the fossil record, rather than being scattered by scavengers, suggests they occurred rapidly and overwhelmed the capacity of decomposers and scavengers to process carcasses. Climate models struggle to fully reproduce the rapidity of observed transitions, suggesting elements of the system aren't fully understood or represented. Most models show gradual drying over millennia, when forced only by orbital changes, but observations require far faster transitions. This discrepancy implies either model deficiencies, missing or misrepresented feedbacks, or additional forcing factors not yet identified. Understanding these rapid transitions is crucial because similar threshold behaviours may affect modern climate systems facing anthropogenic forcing. The speed of green Saharan collapse provides a sobering perspective on ecosystem stability. Even resilient, productive ecosystems can collapse rapidly when critical thresholds are crossed. The gradual forcing, changing orbital parameters, produced a non-linear response, abrupt ecosystem transformation. This relationship between forcing and response represents one of climate science's most important lessons. Systems can appear stable until suddenly they aren't, with transitions occurring faster than adaptation or migration can respond. For the animals and humans of the Green Sahara, the speed of collapse meant catastrophe. Species couldn't evolve new adaptations in centuries. Populations couldn't gradually shift ranges over many generations. Instead, they faced sudden, overwhelming environmental deterioration that demanded immediate responses: migrate rapidly, adapt behaviourally, or perish. Most large mammals failed this test. Only the most adaptable species, those pre-equipped with physiological and behavioural flexibility, survived by fleeing south or adapting to marginal refugia. The rest disappeared, victims of change too rapid for evolution to counter. The refugee migrations. As the Green Sahara collapsed, its displaced fauna didn't simply disappear. Many species migrated, retreating south toward the Sahel and sub-Saharan regions, where conditions remained tolerable. These refugee migrations reshaped African biogeography, compressed populations into smaller ranges, and likely drove ecological changes in receiving regions as influxes of climate migrants competed with resident populations. The fossil and genetic evidence for these movements reveals a dynamic picture of species desperately tracking their required habitats southward, with varying degrees of success. Elephants provide clear evidence for southward range shifts. Genetic studies of modern African elephants show population structure consistent with historical fragmentation and secondary contact between lineages that had been separated. These patterns suggest that populations once distributed continuously across northern and sub-Saharan Africa became isolated as the Sahara dried, with northern populations either perishing or mixing with southern populations during refugial periods or along migration corridors. The absence of unique northern lineages in modern elephants suggests most Saharan populations didn't survive in isolation, but either died out or merge with southern populations. Giraffes show similar patterns. Their current distribution, restricted to sub-Saharan Africa, represents a contracted range compared to their ancient extent into the Sahara. Genetic studies reveal population structure reflecting isolation in different refugial regions during arid periods. While modern giraffes don't preserve distinct Saharan lineages, their genetic diversity patterns suggest historical range contractions and expansions tracking climate oscillations. Some populations likely moved south as the Sahara dried, contributing to modern genetic diversity. Antelope populations show perhaps the clearest migration patterns. Species like addax and scimitar-horned oryx, highly adapted to aridity, actually expanded ranges initially as the Sahara dried. They were pre-adapted to increasing aridity and faced less competition as less drought-tolerant species retreated. However, once aridity exceeded even their tolerances, they too retreated, becoming restricted to Sahel margins. The scimitar-horned oryx formerly ranged across the entire Sahara, but survived historically only in the Sahel, and is now extinct in the wild, a victim of overhunting rather than climate change, but occupying a range dramatically reduced by Saharan desiccation. Carnivores faced different challenges. As prey migrated south, predators had to follow or starve. However, moving into already occupied southern ranges meant competing with resident predator populations. This likely created intense competition that eliminated some populations while others merged. The fossil record is too sparse to track individual carnivore lineages through these transitions, but modern distributions, with no unique Saharan lion or hyena populations, suggest either extinction or complete genetic mixing. Migration routes probably followed the most persistent ecological corridors: river valleys that maintain some vegetation longest, highlands with more reliable rainfall, and chains of oases. Evidence for corridor use comes from the distribution of archaeological sites and fossil localities dating to the transition period. These sites cluster along routes connecting the Sahara to the Sahel, suggesting both humans and animals concentrated along these pathways during migrations. Competition along corridors would have been intense, with different species and populations competing for limited resources in contracting habitats. Some species attempted to persist in Saharan refugia rather than migrating. Archaeological and paleontological evidence shows relic populations of various species surviving around oases, springs, and isolated highlands after surrounding regions became uninhabitable. These populations represent a different strategy, holding on in patches rather than fleeing. However, most such refugial populations eventually failed, isolated and too small to maintain genetic diversity or recover from environmental shocks. Modern Saharan wildlife, mostly desert-adapted species, doesn't include refugial descendants of green Saharan megafauna, suggesting this strategy ultimately failed. The receiving regions, Sahel and sub-Saharan savannas, must have experienced dramatic ecological impacts as climate refugees flooded in. Suddenly, resident populations faced competition from incoming migrants occupying similar niches. Resources that had supported stable populations now had to support both residents and refugees, increasing competition and potentially altering community structure. Unfortunately, the fossil record from receiving regions during this period isn't detailed enough to document these impacts clearly, but ecological principles suggest they must have been substantial. Humans migrated too, following the animals they hunted and the rains they depended on. Genetic studies of modern North African and sub-Saharan populations reveal admixture patterns consistent with population movements during the Saharan climatic transition. Archaeological evidence shows cultural characteristics typical of Saharan pastoral peoples appearing in Sahel regions around the time of desiccation, suggesting population movements carried cultural traditions south. Some groups successfully transitioned, adapting their lifestyles to new environments. Others likely failed, their cultural identities lost as populations fragmented and merged. Not all migrations succeeded. Many populations probably perished during attempts to reach suitable habitats, dying en route from thirst, starvation, predation, or disease. The fossil record is unlikely to capture these failed migrations because animals dying while moving wouldn't form concentrated fossil deposits. However, scattered bones along apparent migration routes hint at the casualties of these desperate journeys. The animals that reached southern refugia were survivors, the lucky, the strong, the adaptable, representing filtered subsets of original populations. The compression of formerly widespread species into contracted ranges had genetic consequences. Populations lost genetic diversity through bottlenecks, periods when population sizes shrank dramatically, eliminating rare genetic variants. This loss of diversity potentially reduced evolutionary flexibility, making populations more vulnerable to future environmental changes. Some species never recovered their former abundance or range sizes, remaining restricted and genetically impoverished, evolutionary ghosts of their green Saharan heyday. The oasis survivors. While most of the Sahara became uninhabitable, scattered oases maintained permanent water and vegetation, serving as islands of life in the expanding desert. These refugia allowed some species and human populations to persist within the Sahara itself rather than migrating south, though under harsh conditions and in dramatically reduced numbers. Understanding these oasis ecosystems and their survivors reveals how life persists in the most marginal environments and what adaptations allow survival when broader regions become uninhabitable. Oases exist where groundwater reaches the surface, creating permanent or semi-permanent water sources that sustain vegetation and wildlife. In the Sahara, oases cluster where geological structures, faults, anticlines, or aquifer outcrops bring deep groundwater to the surface. Some oases have existed continuously for thousands of years, providing stable refugia through multiple climate oscillations. Others are ephemeral, appearing and disappearing as water tables rise and fall with regional climate patterns. The largest oases maintain surprisingly diverse communities. Fossil and subfossil remains from oasis contexts include fish, amphibians, reptiles, birds, and small mammals. Assemblages much richer than the surrounding desert, but impoverished compared to the green Sahara. These communities represent ecological simplifications, with only the most adaptable and hardy species persisting. Food webs shortened, with fewer trophic levels and simpler species interactions. Yet these diminished ecosystems proved remarkably resilient, maintaining structure and function despite hostile surroundings. Vegetation in oases followed predictable patterns controlled by water availability. Date palms dominated wherever water was sufficient, their deep roots accessing groundwater even when surface water was absent. Acacias and tamarisks occupied drier zones, tolerating salinity and seasonal water stress. Grasses and herbs formed understories where conditions permitted. This vegetation structure provided food and shelter for wildlife, creating habitat complexity that supported biodiversity beyond what bare water alone could maintain. Humans occupied oases throughout the arid period, developing cultures intimately tied to these fragile environments. Archaeological sites show continuous or recurring occupation of major oases over thousands of years. Material culture adapted to oasis resources, date palm products for construction and tools, locally available stone for implements, animals and plants from oasis ecosystems for food. Trade became essential, as oases couldn't provide everything required for human survival. Networks of trade routes connected oases, allowing exchange of goods and ideas across the desert. Wildlife using oases developed behavioural adaptations for exploiting these resources. Migratory birds recognised oases as critical stopover points, concentrating there during journeys across the desert. Some bird species became oasis specialists, resident populations that no longer migrated but survived year-round in these isolated habitats. Mammals learned oasis locations and timing, travelling between them or defending territories centred on reliable water. This behavioural knowledge had to be transmitted across generations, making oasis-dependent populations vulnerable to disruptions that broke cultural transmission of critical information. The isolation of oases created genetic and ecological consequences. Populations became fragmented, with limited gene flow between oases separated by uninhabitable desert. This isolation promoted genetic divergence, populations evolving independently in response to local conditions. Some oasis populations developed unique characteristics, though distinguishing true adaptations from random drift in small populations is challenging. Over longer timescales, this isolation might have produced new species, but the relatively recent Saharan desiccation hasn't allowed sufficient time for speciation in most cases. Competition in oases was intense. Limited resources concentrated populations, forcing species into closer proximity than in more extensive habitats. Predators and prey encountered each other more frequently. Herbivores competed for limited vegetation. Species that might have segregated spatially in larger ecosystems were forced into direct competition. This intensity was selected for behavioral flexibility and tolerance, eliminating more specialized or aggressive competitors that couldn't coexist in close quarters. Human impacts on oasis ecosystems intensified as populations concentrated around limited water sources. Overgrazing by domestic herds degraded vegetation. Overharvesting of wood depleted trees. Human hunting reduced wildlife populations, eliminating larger mammals and restricting remaining species to more remote or protected oasis zones. These impacts were probably sustainable at low population densities, but became destructive as human numbers increased, particularly once pastoralism established permanent settlements rather than nomadic movements. Not all oases survived. Many dried out as groundwater tables dropped, either from reduced recharge due to decreased regional rainfall or from overexploitation by human and animal populations. Abandoned oasis sites marked by dead palm stumps, ancient wells, and archaeological remains scar the modern Sahara. These lost oases represent failed refugia where life clung on temporarily before water failed completely. The species and populations depending on them had to relocate or perish, further reducing Saharan biodiversity. Modern Saharan oases represent the descendants of these refugial systems. Their current ecology reflects millennia of survival under extreme conditions, with communities winnowed to only the most adaptable species. The loss of green Saharan megafauna from oases, no elephants or hippos survive there today, shows the limits of refugial strategy. Only small-bodied, highly adaptable species with modest space and resource requirements could persist long-term in these constrained habitats. The larger, more specialized species required expansive ecosystems that oases simply couldn't provide. Will the Sahara green again? The Sahara's current arid state is temporary on geological timescales. The orbital cycles that created the green Sahara continue operating, and future configurations will eventually favor monsoon intensification and renewed greening. However, the timing and nature of future humid periods remain uncertain, complicated by anthropogenic climate change that may alter the system's response to orbital forcing. Understanding whether and when the Sahara might green again requires examining both natural cycles and human influences on the climate system. Orbital mechanics dictate that conditions favouring Saharan greening won't return for roughly 15,000 years. Current orbital parameters place Northern Hemisphere summer at Earth's farthest point from the Sun, minimising seasonal heating contrast and suppressing monsoons. Precession will gradually shift this configuration over coming millennia, eventually creating conditions similar to those that greened the Sahara 10,000 years ago. However, this timeline assumes natural forcing alone, without considering human impacts. Anthropogenic climate change complicates predictions. Rising greenhouse gas concentrations are warming Earth globally, but regional responses vary. Some climate models suggest global warming might actually enhance future Saharan greening by strengthening monsoon circulation as the atmosphere holds more moisture. Other models predict more complex responses where warming shifts atmospheric circulation patterns in ways that maintain or intensify Saharan aridity. Current observations show mixed signals. Some Sahel regions have grown slightly in recent decades, possibly due to increased atmospheric CO2 stimulating plant growth and changing rainfall patterns, but others remain vulnerable to drought. The interaction between orbital forcing and anthropogenic warming is poorly understood. These operate on different timescales. Orbital cycles span tens of thousands of years, while anthropogenic forcing is occurring over centuries, making their combined effects difficult to predict. If warming strengthens monsoons, future humid periods might arrive sooner or be more intense than past cycles. If warming disrupts monsoon dynamics, future greening might be delayed or weakened. Current models don't confidently resolve these scenarios, highlighting critical uncertainties in our understanding of climate system behaviour. Another complicating factor is vegetation feedback. When monsoons eventually strengthen again, vegetation expansion will amplify moisture through evapotranspiration and reduced albedo, just as occurred in previous humid periods. However, if human land use has degraded Sahel and Saharan margin environments through overgrazing, deforestation, or soil degradation, the capacity for vegetation feedback might be reduced. This could create hysteresis, a situation where the system resists transitioning to humid conditions because feedback mechanisms are compromised. Human activities might alternatively facilitate greening. Large-scale irrigation projects drawing on fossil groundwater or renewable sources could create artificial oases that seed broader vegetation expansion. Atmospheric moisture from irrigation evapotranspiration might enhance local rainfall, triggering positive feedback. Some geoengineering proposals suggest deliberately greening the Sahara through massive irrigation and afforestation as a climate change mitigation strategy, capturing atmospheric carbon in vegetation and soils. However, such schemes face enormous practical, economic, and ecological challenges. The ecological implications of future Saharan greening are profound. Species currently restricted to sub-Saharan regions could expand northward, recolonizing formerly occupied territories. However, these wouldn't be the exact same communities that existed during the last humid period. Species compositions will differ, with some species extinct and others newly arrived. Novel ecosystems would develop, assembling from available species in ways that might not have historical precedents. Human impacts will shape future green Saharan ecosystems fundamentally. Unlike 10,000 years ago when human populations were small and technology limited, future greening would occur in a world with billions of people, industrial agriculture, and massive infrastructure. Any habitable Saharan regions would quickly see human exploitation, agriculture, settlement, resource extraction, preventing development of wild ecosystems resembling those of the past. The Green Sahara, if it returns, will be a managed landscape, not a wilderness. Archaeological and ecological knowledge from the previous Green Sahara provides warnings for future scenarios. The rapidity of past collapse shows ecosystem fragility. Productivity and abundance don't guarantee stability. Over-exploitation by humans and their domestic animals probably accelerated past desertification through vegetation removal and soil degradation. If future greening occurs, preventing similar overshoot requires learning from these past mistakes, managing resources sustainably rather than exploiting until collapse. The philosophical question remains whether future greening would truly recreate the Green Sahara or produce something fundamentally different. The species assemblages, ecological relationships, and environmental contexts will differ from those of the Holocene humid period. It might be more accurate to speak of a new Green Sahara, an ecosystem that is productive and vegetated, but ecologically distinct from its predecessors. This semantic distinction matters for conservation and management, emphasizing that restoration or greening doesn't mean recreating the past, but rather creating functional ecosystems adapted to current and future conditions. Ultimately, whether the Sahara greens again depends on complex interactions between orbital mechanics, anthropogenic climate forcing, and ecological feedback. The geological evidence proves the potential exists. Under the right conditions, the Sahara can support rich ecosystems. But the conditions for realizing this potential remain uncertain, clouded by human influences on the climate system. The story of the Green Sahara thus remains unfinished, with future chapters yet to be written by forces both natural and human.